In this section, we're going to learn the chain rule. And the chain rule allows us to take the derivative of a composition of functions. So for example, if we have f of g of x, right? We have the g of x function inside of f of x. But first, let's take a look at example 1. In this example, at least the first part of this example, we have a bicycle that travels forward by 2 meters for every revolution of its wheels. And its wheels are revolving at 3 revolutions per second. What is the speed of the bicycle in meters per second? Well, you may have done some unit analysis at some point in your, maybe in high school. So we can basically just we have the bicycle travels forward by 2 meters for every revolution. Right? That means probably the diameter of the wheel is 2 meters, right? And then if it's traveling at the wheels are revolving at 3 revolutions per second, then if we multiply those two rates, right, the revolutions essentially cancel, and we get 6 meters per second, right? So we're just combining these two rates, right? Or multiplying the two rates to get a new rate. Now in this problem, we have two relationships, really. We've got the relationship between the distance traveled and the revolution of its wheels. So we can think of it as being, let's use S for displacement. S for the distance traveled. And that's a function of the number of revolutions. We'll call that R for revolutions, right? So essentially the distance traveled is a function of the number of revolutions, and the number of revolutions is a function of time, right? So so we can kind of think as this is a composition. If we wanted to know the distance traveled as a function of time, we could do this composition of we could replace R in the function for the displacement with R of t, and then we would get a new function which would have an input of t and an output of the displacement, or the distance traveled, right? So this is essentially a composition of two functions is what we're getting. And then what we've got over here, this is essentially ds dt, or I could, yeah, so it's essentially ds dt. We multiplied the two rates together in order to get a new rate. Now this first 2 meters per revolution, that's essentially the change in S over the change in R, right? If S is the distance and R is the number of revolutions. And then what we did is we multiplied by the change in R over the change in T. Oops, change in T. Right? That's what we did. Essentially what we did. So, so this is leading us to the chain rule, but you see how we took two rates and multiplied them together to effectively get the rate of this composition function. All right, let's do a similar thing here. A different example here. Due to thermal expansion, a steel pipe expands by 0.6 millimeters per degree centigrade, between degrees Celsius. All right, if the temperature is rising by 2 degrees Celsius per hour, what is the expansion rate of the pipe in millimeters per hour? Okay, so we have the length of the pipe is a function of temperature, and then the temperature is a function of time. Now, so we can just multiply these rates. We can take 0.6 millimeters per degrees C times 2 degrees C per hour. And then what we'll have is, you can see the degrees C effectively cancel, and what we have is it will end up with 1.2, and this will be, the units will be millimeters per hour, right? So we took two rates and multiplied them together to get a new rate. And again, we have the length of the pipe. The length of the pipe is a function of temperature. I'll say capital T for temperature. And then we have the temperature as a function of time, all right? Capital T for temperature, lowercase t for time. And if we were to put those together, we would get, we can feed the output of the temperature function into the length function, right? So we're going to get a composition of two functions, and that composition will have an input of time and an output of length. Okay, so what we did here is we just took the change in length over the change in temperature. That was our first rate, right? 0.6 millimeters per degree Celsius times the change in temperature over the change in time. That was the rate at which the temperature was increasing. So what we did is we multiplied two rates together and got a new rate, okay? And essentially it's the rate of the composition function. All right, I'll meet you in the next example.